Hi, this is Team MSSM Penguins, and welcome to our design review. We are a team of 4 members of seniors and juniors from the Maine School of Science and Math, which is a residential school in Limestone, Maine. And we all got recently sent home early due to positive COVID cases, so putting together this presentation was more difficult than we anticipated. So we're presenting to you online. Hope you enjoy. I'm going to pass it off to Ian, who's going to start us off with the SMART requirements.
Hi, so I'm Ian, and we had two goals. One, to scan the ocean for plastic, and two, to geotag the images so that we know the location of the plastic. Therefore, our SMART requirements are as follows. We will create a satellite that scans the ocean for plastic using images and associates a geographical location with the image. Our satellite will take one picture every 10 seconds and check for plastic, keeping only relevant, i.e. containing plastic, photos. The satellite's location will be stored and tracked by the IMU, with each image also sending a set of coordinates. The satellite will operate in low Earth orbit. And the other thing that I did for this assignment was the concept of operations. So pre-launch, we'll make sure the CubeSat is ready and working before launching and test all of the systems. If they fail, we will fix them and then test again. If they succeed, they'll continue on to the launch stage, where if they fail here, there's not much we can do about that. But if they succeed, we'll try to get them into orbit. And if we have a fail here, we can't do much about that either. But if our CubeSat successfully gets into orbit, we'll continue to the action stage. So while it's in orbit, it will take images using the camera and search for signs of plastic in the ocean. Images will then be sent back to mission control if the CubeSat detects plastic. So the CubeSat will perform a self-check to start, and if it fails, it'll communicate with the ground and we'll try to fix it. And if it succeeds, it'll take a picture. If it doesn't find plastic, it'll delete the picture and take a new picture. If it does find plastic, it'll send that picture to the ground. If it fails at taking the image or fails at sending a picture to ground, it will perform another self-check and start that initial process over again.
I'm Henry. This is our system level block diagram. So first, we have our structural subsystem, which consists of our acrylic chassis. Our solar panel and battery are connected to this and form our power subsystem. Then, these are connected to our command subsystem and our Raspberry Pi, which controls the whole CubeSat. Within our data collection subsystem, we have our camera for image capture and our IMU for motion detection. These are fed back into our Raspberry Pi, which processes the data and sends it to the communication subsystem for transmission over Wi-Fi.
So here's our layout. I did a 3D model of what we hope our CubeSat will look like. It was surprisingly hard to figure out how the outer pieces went together for the walls. I couldn't find any instructions, so I based this off of an image I found online of a CubeSat from this competition. What's more important is what's inside though, and beyond what we had from the hardware module with the IMU, the camera, the Raspberry Pi, we also put the battery on top. That's going to be connected to the Raspberry Pi to power it. And then we're going to have the solar panel connected to the battery. So the solar panel is going to be on the outside of the CubeSat, facing toward the sun. And it's going to be charging the battery, hopefully prolonging the time that it can run for. So here's our bill of materials and the cost breakdown. It's going to total up to $185.44 according to the prices now. That's probably going to fluctuate with time. But here's our mass budget. We broke it up into the subsystems and individually measured their weights and tried to get a good estimate for contingency. For a lot of the items, we couldn't find any information that would help us estimate it. So we gave a good 10% contingency just for safety. Otherwise, the contingency is either based off of what was given, a density margin that was given, or a volume and density. So the structure subsystem is gonna weigh about 200 grams. The command and data handling, which includes the Raspberry Pi and the data storage system, that's gonna be 48 grams. The payload, just the camera case, and the IMU is gonna be 15 grams, and the power subsystem, which contains the battery, which is the heaviest, is going to be 200 grams. The total mass is going to be just under 500 grams, which is a lot lower than the weight limit for a 1U CubeSat of 2 kilograms. So we have a lot more room to add weight if we need to. This is our power budget. When we first plugged in the charger tester in between the Raspberry Pi and the battery, it measured that it was gonna take 20 hours to discharge the battery. This would be a minimum of 20 hours. Since we want to be safe, we have that contingency in there. But we discovered that this would be when the Raspberry Pi is idle, it's not doing anything. When it is transmitting or receiving information, especially operating the camera, it will consume a lot more power than that. And so we thought the solar panel would offset that energy consumption a lot to make that battery last longer. But with only one solar panel and a low efficiency, because it's probably not going to face directly at the sun all the time, that's going to offset the battery time at a very low amount. So what we decided was we could turn the Raspberry Pi off when it's not being used. So for example, when it's in an area we've already taken photos of, or it's in that interval between photos, we can turn it off and back on. There is no sleep mode to the Raspberry Pi. I'm gonna figure that out. At full power, everything can operate for 3.25 hours. That's not very long, but if we let it charge for a while, that should prolong how long we can keep it in operation for. We left a placeholder 10 seconds as our imaging interval earlier. That's probably not realistic. We'll do those calculations. We have it planned later. So our link budget and our data budget, we didn't get to those. We were very confused about whether we're supposed to imagine our CubeSat in space and then do the calculations for using the radio waves to transmit and receive data. But we also don't have an antenna for receiving information from the Raspberry Pi. The other option was to use Bluetooth from the lab in the course to simulate this link. But as we weren't sure how to get a lot of the information needed for that in time, we just left these blank. Hopefully your feedback will help clarify some of these problems we had.
Hello, this is Sage Santamena, and I'm going to be talking to you about our software architecture. So looking at our software architecture, we isolated the command center and its computer from the rest of the craft. This command center's responsibility is to issue commands and then process data. And so those issued commands are received by our communications software and hardware before being processed and passed on to the central processor. This central processor takes this information and acts on it. It may do things like monitor the IMU or take pictures. If it wanted to monitor the IMU, it would use a series of IMU management functions that live under the central processor. And so this IMU management could include initialization, beginning calibration, or a shutdown. And so in turn, the IMU needs to be capable of calibration, as well as actually taking the measurements and formatting and logging them. It then needs to report those measurements back up to the central processor, which can act on them. An example of the processor acting on these would be to take pictures, where it communicates to our camera software in order to take a picture, for example, when the attitude of the craft is appropriate in order to take a meaningful picture. The camera then saves these pictures and sends them back to the central processor, which decides whether or not they're meaningful, i.e., whether they contain plastic. And if they do, and these pictures are meaningful, then they're sent back to our communication software, as well as tagged with geolocation information before being sent down to the command center, again, through that same communications software. And so this is what our software architecture looks like here. Hello, I'm Sage Santamena again, and I'm going to be talking about our team's integration and test plan. So the first thing our team did was identify our 6 core components. That's the camera, the IMU, the communication software and hardware, the command center, the actual physical structure, and the central processor. And so starting with the camera, in order to demonstrate its functionality and then work towards its integration, we'd first demonstrate that with hard-coded commands, such as telling the camera that it has received a command to take a picture, it will actually take that picture. Next, we'd want to demonstrate the ability to take these photos on demand by connecting just the camera and the central processor and watching it happen in real time. With the IMU, we'd want to demonstrate realistic readings just by moving it around and formatting that data and then outputting that data to ensure that it works properly. After that, we'd want to demonstrate the ability to communicate realistic readings with the central processor live by connecting just the IMU and the central processor. After that, testing the communications and command center, we'd want to demonstrate that each of these is capable of receiving and sending commands and data. And then we'd want to demonstrate the processor's ability to act on those commands, receiving something to trigger something. From the central processor, we want to start to integrate more systems. We want to demonstrate taking pictures when at an appropriate attitude, and so that involves connecting the central processor, the camera, and the IMU. Or maybe we want to demonstrate sending these captured photos, and so what that requires is the camera, the central processor, the communication software, and the command center. After that, we demonstrate selecting only photos with ocean plastic in them, and that's done with a script on the central processor. From this, we can also demonstrate the initialization and calibration of the IMU on command from ground. And so this would require the communications command center and IMU and central processor. After these things are complete, these systems are integrated, and so we turn towards the structure. With the structure, first we simply want to demonstrate that it fits within the space and mass constraints, then that we can fit all the components into the frame. If those two things are true while the rest of the test plan also proceeds, then the systems are assembled and the integration is complete. And so this is our team's integration and test plan.
This has been Team MSSM. Thank you for watching. We look forward to your feedback.